Hello, everyone. Today we will talk about adder. Today we will study how to build a binary adder. So let's start. So the function of adder is to compute a plus b. And a can be a multiple bits binary. And b can also be a multiple bits binary number. So this is A and this is B. So here is one example. And all the numbers in this slide are decimal numbers. So we can compute 5 plus 7, which is a 12 here. And the result is called sum. So a binary adder is a piece of circuit that can add these two binary numbers. So this is a 4-bit adder, which means that at the maximum, the maximum number can be added by this adder is 4 ones, which is 15. Apparently, 5 and 7 are all smaller than 15. So these two decimal number can be added by a 4-bit adder. And then we need to convert this 5 bits, decimal bits, to its binary representation, which is a 1, 0, 1, 0. 7 will be 0, 3 ones. So let's review how to enable the conversion. So when you try to convert a 5 back to the binary representation, you divide a 5 by 2. You get the result and the remainder. The remainder is a 1. Result is a 2. Continue to divide it by 2. Result is 1. Remainder is 0. And then you continue to divide it by 2. Result is 0. Remainder is 1. So this is 1, 0, 1. The last one here is the most significant bit, which is this one. So by the same algorithm, you can convert 7 to the binary representation. And then we can perform the addition. 1 plus 1, which is a 1, 0. So we have a carry here. This blue symbol indicated the carry. When you calculate the addition for this position, you need to add 0 and 1 and that carry. So 3 numbers, and the result is still 0, 1. We still have a carry here. This is so-called full adder. So for the half adder, we do not need to consider carry in, but here, basically all these 3 bits have a carry in and a carry out. So we have to use a full adder. I will review what's the full adder in the following slide. And then we can write the adder like this. This is a 1-bit adder. For 1-bit adder, we have a full adder. This is so-called full adder. The full adder has 2 inputs, 3 inputs, I'm sorry. two inputs are the operands, and these are two operands, but one of it has a the other one has a carry in. So this is carry in. For the result, we have a sum, we have a carry out. So this is the carry in. This is A, B. A and B are the operands. CI is the carry in. And we also have a CO. CO is a carry out. And the S indicated the sum. So if you have any question, please interrupt me at any time. By 1-bit full adder, we can build a full 4-bit adder to conduct this 4-bit addition. The method to build a 4-bit adder is very simple. You just sequentially connect 4 1-bit full adder together. So you connect the carry out for the least significant bit to the carry in of the next position. And then you always connect the carry out to the carry in for the carry out of the last bit to the carry in for the next bit. So eventually you can have a 4-bit adder. And this is so-called carry ripple adder, because they are connected sequentially. When you do the addition, the critical path is, of course, the carry path. This is the carry path. And this critical path decides the frequency of the adder. And you can see that the critical path is actually proportional to the n. The n is the bit width of your adder. For example, this is the 4-bit adder. And the key component is a 1-bit full adder. By full adder, I mean you have a carry in and a carry out. And this is the one of the output, which is a sum. And this is a so-called truth table. But I, horizontally write this truth table. You can see this is the carry in. This is A, B. These are the inputs. And the S is the sum, which is the output. And I list all the possibility of these inputs here. Since we have 3 inputs, again, we have 8 columns here. Conventionally, we have a vertical truth table, so we have 8 rows. But in this case, we have 8 columns. And here, the column is equivalent to that row. And then we can write the corresponding sum here. This table indicated the carry out. So basically, I can cut this row and paste this row to here. And then we will only have 1 truth table. But here I separated them. We have two truth tables for sum and carry out respectively. And we can also connect, connect them, combine them together into a single truth table. So when we have the truth table, we can use the canonical form to represent the sum and the carry out. And we use the mini terms, the sum of the mini term to represent S, which is also called the sum of the product. We just pick up the row, which can give you an output of 1 as the sum. So this is 1, this is 1, this is 1, this is 1. So we have 4 rows here. For this row, because A is 0, so we write A bar here. B is 0, we write B bar here. C is 1, so we write CI. CI is 1, so we write CI here. So this is the min term which is related to this row. And then we can list all the rows here. And then we can build a circuit to implement this Boolean equation. The circuit is very simple. We have the input of A, B, and C in. We also have the input of A bar, B bar, and the CI bar. And then we use some AND gate to implement the min term and use a OR gate, a large OR gate, to sum them together and then generate the S. And of course, this is not the simplified one. This is, we didn't do the K-map simplification, so this is not the simplified one. This is the original canonical form one. And this is carry out. We basically follow the same steps and generate the canonical forms, the midterm of sum of the midterm of CO. And then this is the piece of circuit. And this one is the circuit representation, which is the simplified circuit representation of the full adder. After the simplification, after we do this K-map, the S, the sum is actually a XOR. This is an XOR symbol. XOR B and XOR C in. So A XOR B is actually A and B plus all A bar. I'm sorry, this is A bar and B and all A and B bar. So this XOR operation can be converted to this Boolean representation. And the carry out can be converted, simplified to this format. So you can see that these two actually share the same, share some part, which is A XOR B. So you can implement A XOR B first, and then share the same output of A XOR B, and use it for the S and use it for the C out too. This is exactly what I'm trying to do here. So this is the XOR gate. When I generated the A XOR B by this gate, the result is here on this line. I connected this line to the next XOR gate to generate a S. And I also use this wire to connect it to the AND gate. Yes, AND gate to implement this part. So this is the the meaning of this piece of circuit. And this is A and B. And this is the OR operation here. Again, in order to have this piece of circuit, you need to have a XOR gate. That's the critical part. And each XOR gate can be broken into multiple AND and OR gates like this. And then we can rewrite the full adder like this. This is the component which can generate a cout, carry out. And this is the component which can generate the sum. Both of these two components have the same inputs, which is A, B, and C carry in. And then we can combine them together as a full adder. And then we can sequentially connect the full adder, one bit full adder, into a multiple bits binary adder. This is how we build the multiple bits adder. And this adder is a so-called ripple carry adder. And when we have two inputs here, we just connect the inputs to corresponding position in the circuit.
Excuse me.
Yes.
Is the carry out from the most significant bit attached to the carry in of the least significant adder there?
No.
Okay, just verifying.
You can see that this is the carry out of the most significant bit, MSB. And this is the carry in of the least significant bit. I will give you more details for these two bits. Basically, this one connected to nothing. For this bit, for this wire, we have some other function. We need to use this wire to implement another very important function.
Okay, thank you.
And then we can rewrite the adder like this. So you can see we actually have the carry in for the least significant bit, and and have a carry out for the most significant bit here. We don't connect them together. And the next step is now we can only do the addition. How to do the subtraction? If we want to do the subtraction, we need to use the 2's complement number. Again, if you have any difficulty in these slides, you can review the slides of the binary number representation. I explained what's the signed number, unsigned number, signed number, and the 2's complement number here. So by 4 bits, for unsigned number, we can represent these numbers. For the signed number, we can represent these numbers. The difference between 2's complement and the signed number is that for the signed number, we have a positive 0 and a minor 0 and negative 0. This is redundant. 2's complement has only 1 0. So 2's complement number can represent a larger range, more numbers with the same bits. So the subtraction will be converted to A minus B will be converted to A plus minus B. This is negative B. The negative B will be represented by the 2's complement form of the B. And then we just directly do the addition between them. So, the procedure to convert a number to its 2's complement representation is that we do for the B, we do inversion for each bit of the B. And then this is the first step. The second step is to add a 1 to the least significant bit of the bit. So in order to implement these two steps, we add a inverter to here. So these inverters are used to implement this inversion operation. So we basically need to invert each bit of the bit. And we need to add a 1 to the least significant bit of B. So we connect the carry in of the least significant bit. We should connect a 1 to the least significant bit of the carry in of the least significant bit. I'm sorry. So because this is 0, and we have an inverter here, so here is a 1, and of course this is 1. So by this 1 and these inverters, we can, automatically implement this 2 complements of the B. Okay, so sometimes we may not have these inverter. So in this case, we use the XOR gate to serve as an inverter. Again, A XOR B. I just explained this equation in previous slides. Equals to A and B bar plus A bar and B. So this is what the XOR operation about. So if I do something like this, if I assign a 1 to the B, so what will happen if A XOR 1? So you can plug a 1 to these positions. If B is 1, then 1 bar is 0, so we don't have this. Any number multiply or add 0 is still a 0, so we don't have this part. And any number multiply 1, which is, still that number is A bar. So if I use A XOR 1, my result is A bar. If I use A XOR 0, what will I will have? So I can plug this 0 to this B bar. 0 bar is 1, so I got an A here. And any number multiply 0. B is 0, is still 0, so I add a 0, which is still A. So by the one XOR gate, I can have the A bar and I can have the A bar and the A. So by a single XOR gate, I can have both A and A bar, which means that in this example, I can have the B and B bar. And this, the other input is actually a control bit. If I set the other input here as A, then this gate will be a NOT gate. If I set the other input as 0, then it's a normal wire, which is a so-called transparent gate. It doesn't have any impact on this wire, on the value of this side. So in this way, I can use this XOR gate. So I just replace all the NOR gate to an XOR gate and connect them together. And this control bit is actually connected together. And I rename this control bit as a sum. So if I want to do a subtraction, I just set the sum as 1. So back to this slide. If I set 1, this input bit as 1, then the XOR gate will be a NOT gate. When I set this as 1, these gate will be changed to NOT gates. And again, I set a XOR gate here. When I set this as a 1, I will have 0 XOR 1. 0 XOR 1. This is 1, still 0, plus 0, not 0, it's just 1, and then 1. So I have a 1 here. Then this is 1. 0 XOR 1, which is still 1. So I connect the least significant bit of the carry in of the least significant bit to 1. This is this one, okay? And then these gates will be converted to NOT gates. So in this way, I can implement the 2's complement conversion by only XOR gates, these XOR gates. And these are the full adders. So you just add this A and the minus B together. So in this way, this piece of circuit can do the subtraction. And again, if I want to do an addition, I will set this sum back to 0. So if I set this sum as a 0, and these XOR gates will be transparent. 0 XOR 0, which is still a 0. So the carry in of the least significant bit is 0. So I didn't modify anything here. It's just a very normal carry ripple adder here. So I explained what will happen if I set this sum to 1. What will happen if I set this sum as a 0. So the only thing in this figure I didn't explain is this part. So let me explain that small part. Again, I think we have this slide in the 2's complement representation slides before. If I want to calculate these, this is an addition. I add a positive number with another positive number. I convert them to binary bits. Each of them is represented by 8 bits. These are 8 bits, 4 bits, 4 bits. And then we just need to add them together like this. These circles indicate the carry, and this is results. And you can try to repeat this process yourself. But the problem is that you can see the most significant bit here is a 1. In the definition of the 2's complement number, if the most significant bit is 1, then this number is a negative number. That's impossible because one positive number plus another positive number cannot be a negative number. So this is the reason we have an error here. And this error is a so-called overflow. The overflow means we cannot represent a very large number by only a few bits, or we want to represent a very small number by only a few bits. So we need to have more bits to correctly represent this number. So back to this example, the sum should be 130, or the correct result should be this number. The problem here is that we cannot represent this number by only 8 bits. In order to correctly represent this number, at least we need 9 bits. So we need to detect a so-called overflow. And these are the cases when the overflow happens. If we try to sum two positive numbers, the negative we get a negative result. If we try to sum two negative numbers, we get a positive result. These are the two cases we need to be careful. We need to pay more attention on these two. So the overflow can be detected by this piece of circuit. We just need to use the carry in of the most significant bit, XOR the carry out of the most significant bit to detect the overflow. If they are the same, we are fine. Otherwise, if they are different, then an overflow happens. So the overflow can be represented by the carry in, C in of the most significant bit XOR the C out of the most significant bit. You can check this example. These are the examples. For example, we sum two negative numbers together. And then we have this. The carry out of the most significant bit is 1. The carry in is still 1. So in this case, we are fine. There's no overflow. But for this example, the carry out is 1, but the carry in is 0. When there's no carry in, so carry in is 0. 1 XOR 0. We got a 1. So overflow happened. So you can review these two examples yourself. So in this lecture, we talk about binary addition and how to use truth table canonical form to implement a binary adder to do multiple bits addition and multiple bits subtraction. And also in this lecture, we introduce a very simple adder, which is so-called a ripple carry adder. The disadvantage of this adder is, we have a very large critical path. By a very long critical path, we cannot, make this adder operated at a very high frequency. So you can see how to compute the critical path of this, timing of the critical path of this ripple carry adder here. So basically, the critical path length is proportional to the bits, how many bits this adder can add. And I will assign a homework for you guys to implement a carry ripple adder. In the next lecture, I will present the deep learning. So for your projects, you can actually reuse this carry ripple adder in your projects, because in the next lecture, I will show you how to use an adder to do the inference of a neural network. Any question? So if no question, we will stop today. Thank you very much.
Thank you.
Thank you.